Muy bien. Les damos una cordial bienvenida a todos por estar aquí con nosotros en esta reunión de la División de Enseñanza de la Sociedad Mexicana de Física, que vamos a tener un par de días con presentaciones, algunos trabajos, y vamos a comenzar el día de hoy con nuestro primer conferencista, que es el doctor David Sokoloff. David fue presidente de la Asociación Americana de Profesores de, de Física de ahí de los Estados Unidos. Esta pues es la organización más grande del planeta de profesores de física y con mucha tradición y bueno, ustedes conocen ya acerca de lo que es la APT y ha tenido pues siempre David una pues disposición muy buena de participar con los colegas latinoamericanos. Como hace unos momentos estaba saludando a los colegas de Guayaquil y bueno, de otros países. David se ha distinguido por muchos aportes a lo que es la enseñanza de la física. Desde los años 90, junto con Ron Thornton, eh, desarrollaron lo que se conoce como clases demostrativas interactivas. Y bueno, se han hecho pues ya modificaciones de esta metodología, diferentes aplicaciones y pues esto ha sido muy interesante y ha habido una gran respuesta por la comunidad docente de física. Y bueno, ahora él nos va a explicar en cuanto a la experiencia que se ha tenido cuando pues hemos estado en lo que es la pandemia y que se ha tenido que adaptar este tipo de metodologías que pues realmente son presenciales y que van bajo el eslogan de hand-ons, mind-ons, ¿no? De tener las manos ocupadas y la mente también activa de los estudiantes. Entonces, es para nosotros un honor el tener a David Sokoloff, que es una autoridad en cuanto a esto del aprendizaje activo de la física. Él pues nos va a exponer ahora una conferencia muy interesante que sin duda pues será de utilidad para ustedes, para conocer pues esta metodología que aún pues se está aplicando tanto presencial como a distancia. Y David, welcome to our meeting. I have I have a brief introduction of you, of your trajectory, and we are very honored to with your presence in this meeting of the Mexican Physical Society. And we can start. The time is yours and you
Okay.
can make your presentation.
All right, let me, whoops. Of course, I just clicked on something. Wait 1 second. I have to bring, there, okay. Let me share my screen. And okay, you can see my PowerPoint?
Yes.
Yes, okay,
Yes, we
good.
said.
All right. So, I thank Cesar for inviting me. This is a joke between me and Cesar because I have many times promised that I would learn Spanish and present in Spanish, and maybe next time. But thank you for the invitation, Cesar. I will try to speak slowly in English, and Cesar says that my talk will be posted. It's being recorded, and you will be able to look at it even slower at your pace afterwards if you desire to do so. I want to thank my collaborators, Priscilla Laws of Dickinson College and Ronald Thornton of Tufts University for actually 37 plus years of physics education research work. And our group, the activity-based physics group, was awarded the 2010 American Physical Society Excellence in Physics Education Award. And also in the US, the National Science Foundation and the US Department of Education funded our work. So here's an outline of my talk. I will talk a little bit about the problem addressed, characteristics of active learning environments, in-class interactive lecture demonstrations, and then the main topic of my talk, home-adapted interactive lecture demonstrations, design features, multimedia resources that were used, and a few examples for you, and then wrap up and questions. So, the problem addressed. When students come into an introductory physics course, they often have definite views about physics because they've done many experiments in physics as part of their life experiences, walking, running, riding bicycles, driving cars. And these views are often not correct. Physics education research has demonstrated that if the students take a traditionally taught course, they will leave the course pretty much with the same incorrect views, regardless of the skill of the instructor. So if no effort is made to engage physics students in the learning process, they will not learn. And with the pandemic of the last few years, many learning environments became even worse than traditional. So the question for this talk is, can we maintain effective active learning for our students in distance learning? So I like this cartoon. It summarizes the physics education research. I will not learn concepts in physics class. Of course, it's not willful by the students. It's just a question of strategies. Or if you know Sheldon from popular American television show, how can they possibly not learn from my perfect lectures? The proposed solution, active learning environments, not replacing, but complementing more quantitative work. So, what are the characteristics of active learning environments? In active learning environments, the instructor's role is as a guide, not as the authority. Students construct their knowledge from observations as much as possible. We use the learning cycle of prediction, observation, comparison to challenge students' beliefs. We encourage students to collaborate with their peers. And the laboratory is often used as a place to learn basic concepts rather than to confirm what was learned in lecture. And finally, physics education research validated active learning materials are used. So, in a traditional lecture, information is only flowing from the professor to the students, and the students might rebel and say, stop, my brain is full. But in actuality, the research says they don't learn very much from lectures and they don't change their views. So how can we change that in a lecture class? So the question 30 years ago was, can an active learning environment be created in a large or small lecture? And the answer 30 years ago was yes, through the use of interactive lecture demonstrations. So let me give you an example of in-class interactive lecture demonstrations. And this example is image formation. So the first step is that the presenter, the lecturer, describes the demonstration without showing the results. So here is, you can see the apparatus for demonstrating image formation. And I'll say a bit more about this in a little while. The students are asked to record their individual predictions on a prediction sheet. Don't try to read this. It basically, demonstration number 1 says that there's an object, there's a converging lens, the object is clearly outside the focal point, and they're asked to draw a simple ray diagram and to show where the image is formed. And then they're asked, is the image real or virtual? You'll notice there's a place on the top for the student's name, and it says hand in this sheet. And it is true that prediction sheets are collected at the end of class after we've done all the demonstrations, but predictions are never graded. Predictions are what the students think at the moment they make the prediction, based on what they know up until then. Step number 3, ask the class to engage in small group discussions, compare their predictions, and see if they can reach a consensus. And this happens to be a class I did interactive lecture demonstrations with in India. And you can see the students are very animated discussing with each other. Step number 4, elicit common predictions from the whole class. So ask for volunteers to share their predictions. This is especially important with a very large class. Whoops. Step number 5. At this point, the students can change their prediction if they like on their prediction sheet. And then step number 6, carry out the demonstration and display the results. So let me show you how this is done for image formation. You see the apparatus consists of an object and 2 small light bulbs, which are point sources of light. A large acrylic lens in front of the object. When the lights are lighted, you see where the light is focused by the lens, and this indicates, if you examine it carefully, that the image is located there and that the image is inverted. And of course, if we put a piece of paper there, we would see that the light is actually focused, and therefore it is a real image. Step number 7, ask for volunteers to discuss the results in the context of the demonstration. And this is actually done in Japan with a large group of instructors, actually they were my students, of course. And the students then can fill out a result sheet. The result sheet looks exactly like the prediction sheet, only the students can take it home with them. Before we look at the last step, step number 8, let's go on to demonstration number 2. In demonstration number 2 of this sequence, the students are asked, what will happen if we block the top half of the lens with a card? How will this change the ray diagram, and how will this change the image? Students again go through the steps, make their predictions, discuss them, etc. And then we show them the result. And when we block the top half of the lens with a card, what we see is the same image, the same inverted image, the whole image, and it is dimmer. And we ask for volunteers to describe the result and why it is dimmer. And of course, it is dimmer because there's less light reaching the image. And then finally, just to show you the last demonstration in this sequence of 3 demonstrations, what will happen if we block half of the object? And in this case, if we block half of the object, half of the image is gone. And if we ask students, again, volunteers, why is this different? And hopefully we can guide them to the answer, this is different because there's no light reaching the image from that half of the object. And then step number 8, we ask if the students can describe an analogous situation with a similar result or an application of this phenomenon. And in this case, we hope and we guide students to answer that in a camera aperture or the iris of our eyes, when they close down to block part of the lens, we still see the entire image. And this procedure of 8 steps is followed for each of the short lecture demonstrations in a sequence of interactive lecture demonstrations. So there is the procedure for in-class ILDs. Of course, the important question, if we try any new strategy in teaching, is, do students learn better? And we have done research. We've developed a light and optics conceptual evaluation. It's a research-validated multiple choice test. And I'm not going to go into all the details of it. You can find them in papers that are referenced on the links that I'm going to give you later. We have post-traditional instruction, only a 20% gain as indicated on the light and optics conceptual evaluation. And post 1 hour of interactive lecture demonstrations like the ones I showed you, an 80% gain from the pretest. So a very dramatic improvement just from 1 hour of focusing using interactive methods, active learning methods. Why are active learning environments effective? Well, when you ask students to make predictions, it requires them to consider their knowledge before making observations of the physical world. So they become aware of what it is that they think about it before they make an observation. By making a prediction, defending their prediction to their peers, and writing down the prediction on a sheet of paper that will be collected, The students are engaged. They want to know the result. And so when they see the result of the experiment and see that, as is most often the case, the result is different from what they predicted, there's a disequilibrium, the psychologists would say. The prediction is different from the result, and it inspires them to want to learn, why are those different? And then we have them construct their knowledge from observations of the physical world displayed in understandable ways. Just one question about the apparatus. Why do we use individual light bulbs rather than use a ray box? And the answer to that question is very simple. Physics education research that was done actually a number of years ago now shows that students don't understand that an infinite number of rays emanate from each point on an object. There's a cone of light from any point on the object. And it is the light from that cone that actually hits the lens that gets focused to a corresponding point on the image. Because they think about a small number of rays, partly because they draw ray diagrams, it leads them to conceptual problems. So for example, if they drew two rays in a ray diagram and they block half the lens, they block one of the two rays. And then they are confused. Many students think if you block one ray, you only see half the image. If you block one ray, there will be no image because no rays will intersect. So we use all of the light from point sources. Another question that we should answer is, what about regular demonstrations? I don't know about Mexico, but in the US, it's very common for lecturers to do demonstrations. And so do students learn from traditional demonstrations, whether they're presented live or presented virtually? And research from Eric Mazur's Physics Education Research Group at Harvard University and other research studies have shown that the majority of students don't learn from demonstrations unless they are engaged first. And that means by making a prediction or somehow being engaged by the demonstration before the demonstration is shown. There is a book called Interactive Lecture Demonstrations. It has demonstrations on 28 different topics, including student prediction and result sheets, instructor's guides, teacher preparation notes, and the 8-step process. I will put right now in the Zoom chat, I hope, I'll try to do it, a link to download the entire book. The book, of course, is in English, but I will also put a link to download prediction and results sheets that over the years have been translated into Spanish. There's actually quite a number of them, maybe about half of the demonstrations in the book have been translated into Spanish. So let me try to do that. If you'll bear with me for 1 second. And I always have trouble finding the window again. Okay, whoops. Whoops. This. Okay. Sorry. I want to make sure I do this before I forget. Okay, so there's 3 links. I'll tell you what the other link is a little bit later. Okay, there's the chat. All right. Um, where did that? Okay, I'm not seeing how to get, oh, maybe here. No. How do I get to the chat? Okay, I will try again later, but in the meantime, I will be sure to give this to Cesar and he will make it available to you. So let me resume my share and go back to my talk. It's okay, you can see it?
Yes, David.
Okay, good. All right, anyway, you will definitely have this book available to you. So let's get to the second topic of my talk. During the pandemic, of course, at least in the US, we were not meeting students live. And so the question was, can an active learning environment be created for students working at home? So I, about 3 years ago, 2.5 years ago, decided I would try to put the interactive lecture demonstrations online and available for students. So here are the design features of what I ended up calling home-adapted ILDs. So there's 26 sets of them now online, available to use for free. Unfortunately, they are only in English, but I welcome somebody to translate them if somebody wants to do that. They are based on the in-class ones. They introduce or clarify topics. They can be used as one PER validated component of a course. Students work alone online, and because I knew that many instructors did not use Zoom very much in the past, I didn't want to burden them with having to figure out how to use breakout rooms. So I put in no requirement of group work. But of course, you could add group work if you wanted to. I'm sorry, there you go. Yeah. They use multimedia available online for students' observations. And so there are photos and videos of experiments. There are real-time videos of the evolution of graphs from computer-based measurements. And there are PhETs and Physlet simulations. And it was amazing to me how much was available to do this back when I started doing it. So to look at these home-adapted ILDs, there is a web page, and I'm going to go to that web page. And again, I will give you this link along with the other two links. So you click on the link, and that is the home-adapted ILDs web page. And there's a list of 26 different sets of ILDs. There's some information on labs. There's some information, background on ILDs, and so on, which you can find at that link. Okay, I'm going to go back to my talk, and I'm going to show you some examples of home-adapted ILDs. The first one is just to show you how the image formation with lenses ILDs that we just looked at is done as a virtually at home. So I click on that link, which is the link from that page, and you see that what comes up is something that looks like the prediction sheet, only it's not quite the prediction sheet. It's actually an instruction sheet. There is a prediction sheet, and I can download a Word copy of the prediction sheet by clicking here. I'm not going to do that now, but I click it and the students download a copy of the prediction sheet. If you look at this, it's exactly the same demonstration as I just showed you. It has a little bit different wording, and there are places in here with links. So for example, it says after you've made your prediction, click to observe the images. So I click here, and there's the apparatus. And I click here, and there is the image. So after the students have made their predictions, they're able to view these. But there's more, because I found that there's a very nice Fizzlet simulation. So if we go to that simulation, and go to this is a part of the simulation. You notice there's a point source on the object, and you can move the point source up and down and see what happens on the image. So that's incorporated. And then after they've done this, there's another part of that simulation where I can set up a converging lens, and I can look at a ray diagram.
David, we are not seeing the simulation.
Really?
Yes.
You're not seeing it at all?
No. The slide is only with the title, but there
You're
is
just
no
seeing my
simulation.
shop.
No.
Okay, that's very strange, because I've done this many times and they always could see it. Okay, let me do something. Sorry about that. Because it's running. Oh, I know why. Okay. My fault. I did the wrong thing. I didn't really share my screen. I shared my PowerPoint. Okay, I will fix it. Now let's see if this works. You see it now?
Yes.
Okay, so this was the first one. Sorry about that. You can move the point source up and down on the object, and it shows what happens on the image. I thought that was very nice. And then if I go to ray diagram and choose converging lens, I can see a ray diagram. So I incorporated those into the simulation. Okay, I'm going to get rid of this. I'm sorry, into the demonstration. So that gives you an idea of what image formation with lenses looks like. Let's summarize the steps, because they're slightly different. The student downloads the prediction sheet. They read the written description of the demonstration, and they may view a photo, a sketch, or a video of the apparatus. They record their individual predictions on the prediction sheet. Only after recording the predictions, the students observe the demonstration as a video, photo, or simulation and see the results. They describe the result on the prediction sheet, and they may be asked a number of probing questions to guide them through critical thinking about the result. And this procedure is followed for each of the lecture demonstrations in the home adapted ILD sequence. Let me show you another one to show you a different, show you a different use of multimedia. So this one is force and motion, Newton's third law. Again, you see, you click here, you can see this okay? Yes? Okay, yes?
Yes, David.
Again, you can download the prediction sheet. The first set of demonstrations involves something that's often confusing to students, and that is the difference between Newton's second law and Newton's third law. So in this set of demonstrations, 1, 2, and 3, they are pushing a block that starts at rest, then is moving at a constant velocity, and then slows down and stops. And they're asked to compare the applied force to the force exerted by the block back on the hand in all three parts of that motion. So let's look at a video to see what they can look at to observe. And let's see, let's do it. So these are what are called I/O labs. I won't go into description, but they are little computer-based lab devices that have force probes in them. And you see that during the entire motion, the applied force and the force applied by the cart on the right back on the one on the left are exactly equal and opposite. No matter whether the thing is speeding up, moving at a constant speed, or slowing down. Oops. Then, of course, as we do in the in-class ILDs, we move on to a number of collisions where we have a number of different collisions between carts. And I will look at the most difficult one for students. And this is a collision where a massive cart, we could call it a truck, a big truck, crashes into a little car, a light cart. And the light cart is at rest. The big truck is moving. So it's a very asymmetrical collision. And we ask the students, what about the force that the truck exerts on the car compared to the force that the car exerts back on the truck? And again, we have a video made with these I/O labs, and you see on the left, the truck, and there's the collision, and there are the forces. And again, you can see that they're equal and opposite. So these are very, very good demonstrations of Newton's third law. And we have learned from the in-class ILDs that students finally understand Newton's third law when they have done these demonstrations. I'm going to show you one more example. And this one is heat engine. And again, this is a set of demonstrations that we've done for many years as part of our in-class ILDs. It explores a heat engine and the processes on a PV diagram by showing a real heat engine. And the heat engine is made with a glass syringe. And I'll show you what it looks like. So let me go to that demonstration. Again, there's the instruction sheet, and here is the apparatus. And you see there is a glass syringe which has air in it. There's a mass on top of the glass syringe. So what this heat engine does is it lifts the mass. We have sorry. Okay. We have a hot reservoir, which has hot water in it, a cold reservoir, which has ice water in it. Okay. And so there's the heat engine. There is a pressure probe that will measure the pressure, and I will enter the volume of the gas manually. So let me show you a video of the heat engine. You see that the pressure will be displayed on the computer screen. So I enter the volume to start with. Now I take the gas and I put it in the hot reservoir, and notice that the mass is being pushed upward by this engine. Again, I enter the new volume. And by the way, you'll notice that this is an isobaric process because the pressure is atmospheric pressure in both cases. Okay, now I remove the mass and the piston went up a little bit more. I put in the new volume. And now I go back to the cold reservoir. And you see the piston is coming down. And then finally, I put the mass back on again to complete the cycle. And I enter the new volume. And there is the PV cycle for this heat engine going through one full cycle. The way that this can be done is that a glass syringe of this type, it's just a medical syringe, has very, very low friction if you keep it clean. Okay, so there is a third example of home-adapted ILDs. So let me say a few more things about them. They incorporate the prediction, observation, and comparison phase of ILDs. They're based on the in-class versions. Oops. Quality multimedia is substituted for live demonstrations. They're easily used immediately because they require no equipment. Now, they have not been research validated. There have been no opportunities to do that over the last 3 years. So if anybody wants to, I welcome it. They're not completely refined, so feedback to improve them is certainly welcome. And they're not translated into Spanish as of this point. Oops. So I don't know whether our students have loved doing virtual work. The studies show that they haven't, but hopefully something where they actually are interacting and learning actively from observations will help with that. So there's more information at the Home Adapted ILD webpage. And again, I will give you that link. Thank you for your attention. And I would be happy to answer any questions that you have. And as so please feel free to mute yourself. As we do that, I'm going to try to see how I get the full panel back so I can put something in the chat. I don't know.
Muy bien. Ahora
there it is.
es el tiempo para las preguntas. Si gustan hacerla, David, directamente en inglés o en español, si no se sienten muy a gusto o en el chat, ¿no? Como ustedes gusten. Para no atrasarnos mucho, tenemos 15 minutos para preguntas.
So the links are now in the chat.
Sí, ya les puso la liga del libro en el chat.
Any questions?
¿Alguna pregunta? Dice...
You're welcome, Pilar.
Hay una pregunta del doctor Rubén Sánchez. How the students felt during the classes? Let me see the chat. Okay, David. How's your students felt during the practices of the after learning?
With home adapted ILDs? Is that the question? Feel free to unmute and speak if you want to. Don't worry if you think your English is not good, because you believe me, if you heard my Spanish, you would not be shy at all. My Spanish is terrible. Okay, yes, I see a hand. What would you like?
I was just wondering whether you use these kind of methods all the time in the class, like 100% for everything, or whether you switch between traditional style of presenting material and then doing the one which you showed us now.
Okay, good question. So when we are doing in-class ILDs, no, we don't do it in every class. So if I am teaching a class that has 3 lectures each week, then normally I will have 1 full lecture that is ILDs. And often I would do that as the first lecture of the week on Monday, and I would use it to introduce concepts as often as I could. And the reason for that, and then the other 2 lectures might be regular lectures. They might be, I might incorporate some active learning in them, but the point is that the other lectures can build on what I did actively in the first lecture, okay? For home adapted ILDs, I have never used them with a class because I haven't been teaching. I am retired, but I envision that they would be used as perhaps homework, as maybe pre-lecture activities. So you would assign students to do these before they attended class. Now that we are meeting students live, they could very well be used as homework, or for pre-lectures, as I said. So yeah, but I don't, when I have taught introductory physics, I don't do active learning in every lecture, but I do tend to interact a lot with the students during the class. I ask a lot of questions, but I do ILDs once a week. Other questions?
¿Alguien más que quiera hacer una pregunta?
Me, I want to make some question. It's about the preschool level. With the proper preparation, it is possible to carry out the interactive classes at the preschool level. Is this possible, in that stage?
Okay, can you define for me what you mean? What age are we talking about?
Probably around 3 years, from 3 years up to 6 before the primary school.
Okay, let me answer that question by first saying, of course, I have no experience doing that, or very, very limited experience. My partner Christine is an expert in science and math education at that level. And she is very much in favor of students doing activities and learning from their activities. In other words, a constructivist point of view about learning. So my personal answer, naive answer to your question is that yes, students can learn through active learning at that age if the activities you do with them are age appropriate. And I invite you to read her books. If you like, if you email me, I will send you those references because she is truly an expert on this. Okay.
Okay, thank you very much. Because sometimes a lot of students, I have been working with kids since 5 years ago, and they does a lot of questions that is quite difficult to respond because the answers also need to be simple.
Sure.
Otherwise, they will not understand. But
Exactly.
I think it's possible. I like the possibility using the demonstration classes. Thank you very much.
Yes, and I'll add to my answer that the youngest students that I have worked with, I have done things like interactive lecture demonstrations when my son, who is now will be 26 years old in June, when he was in the 5th grade, which means he was about 9 or 10 years old, I did some interactive lecture demonstrations with his class. And I have to say that the students were able to examine the demonstrations and come up with some very interesting ideas. But of course, obviously, you have to be very, very careful with the language because it has to be at a level, at the appropriate level for them.
Thank you very much.
Yes, you're welcome.
David, we have another question. It's about the motivation. One of the participants said that the students lose interest early, especially that whose achievements are lower. How do you keep them motivated?
During the pandemic, is that what we were talking about?
I suppose that in the pandemic and post-pandemic and pre-pandemic, all the time, no? Because this is a very general, this is a general problem.
Okay, so let me say that in a traditional learning environment, we basically assume that the teacher is the expert and the teacher will explain everything to the students and they will absorb everything that the teacher says and they will understand and learn it. That's a very simplified view of traditional instruction. In an active learning environment, we assume that the students are able to learn from their observations. We might need to guide them to be sure that they observe what we know they will most likely learn from, but we don't tell them the answer. We get them to discover the answers. Now, so the thing that keeps students interested is the fact that they are always making observations or frequently making observations, and the observations are often surprising to them because they're different than what they would have predicted. Now, I will just say to you that in all the years that I taught introductory physics and that I did interactive lecture demonstrations, that at the end of the year, when students filled out course evaluations, and they were asked, what did you like the most in Professor Sokoloff's class? And the answer, by far and away, was interactive lecture demonstrations. And I'm not naive. I know that one reason why they like interactive lecture demonstrations is because when they take an exam from me, I often put conceptual questions on the exam. And they know that what they learn from the interactive lecture demonstrations helps them to answer the conceptual questions correctly. And students are often very motivated by doing correctly on exams. So I'm not naive to say maybe they don't love my interactive lecture demonstrations. Maybe they don't love me as their teacher, but they love learning things that will help them do well. So my answer to you is, number one motivation, they are doing things, they are observing things. And they are engaged in that. This is much more interesting than just listening and much more effective. And number two, it helps them to be able to do well in the course. So this is how they get motivation. During the pandemic, I have not taught. And I said right from the beginning, I thought, oh my God, I'm so glad that I'm no longer teaching, because what would I do? But I think that home adapted ILDs can help with this, because again, they inspire students to make observations. And to me, look, I spent quite a bit of time during the pandemic making those, but frankly, I had a lot of time on my hands during the pandemic. So I had a lot of time to do it. It was enjoyable, but I also think that it is a resource that students can use and be interested, because they are looking at the physical world. They are not just listening to somebody. That's the problem with Zoom. The problem with lectures on Zoom is that it's even more passive, unless you make an effort to make it less passive. So, and I apologize, because I have done workshops on Zoom during the last 3 years where I made them more interactive, and had participants make predictions, and had participants go into breakout rooms. And I just decided, because I had less time to prepare this, and also because of the language difference, that I would just show you rather than have you participate. So I apologize for that, but try them with your students, and let me know what happens.
Okay, David, thank you very much for your invitation and for your talk. And I'm sure that people are interested to work with you, to know what is the experience at home using introduction lecture demonstrations. Thank you very much.
Thank you. You're welcome. De nada.
Bien.
Adiós.
Hasta luego. Agradecemos mucho a David y a todos ustedes su participación.